just want to start with welcoming everybody to this model-based systems engineering session, which is part of the growing systems engineering and design topic of the design conference. I'm Felician Campean. I'm professor of automotive reliability engineering at the University of Bradford in the UK. And again, it is my pleasure to welcome, first of all, the speakers. So we have representatives. So we have speakers from all the papers here with us, and all the other colleagues that have joined this session. So in order to save time and to gain a lot more time for the discussion, I'm not gonna go through a detailed introduction of each of the paper and each of the speakers. So we had a brief discussion at the beginning, and the point was that the speakers are doing a small intro part of their talk. So we have 5 very interesting papers. I'm going to suggest that we get going and listen to the papers. What I would like to ask everybody in the session is try to write your questions in the chat. What I've seen is that works very, very well. And that is both because we're building up the deck of questions that we want to have discussion on after the presentations, but it's also giving us an opportunity to maybe look at topics going across the presentation. So building up on questions that come in the chat, looking across the presentations. I think that's particularly relevant on session like this one, where the papers are actually very well integrated in the session. So please write your questions in the chat. Of course, you will also have the opportunity to come in at the end after the session and to ask the question directly, so to say. So without further ado, I suggest that we move on with listening to the presentations, to the recorded presentation, starting with the first presentation from Ralf Stetter. So Maria, if you play there.
Welcome to my presentation, Capturing the Design Rationale in Model-Based Systems Engineering of Geo-Stations. My name is Ralf Stetter. My co-authors from the University Ravensburg-Weingarten in the south of Germany are Andreas Zech and Markus. And then there's also Stephan Rudolph, who is at the University of Stuttgart. In my talk, I will talk a bit about the underlying research project. Then I will talk about how model-based systems engineering with graph-based design languages works. I will present the product development process of Geo-Stations, and I will talk about design rationale for the definition of a joining sequence, then for clamping and centering positions, and then for clamping and centering units. So the underlying research project is called Digital Product Lifecycle, and there is a block talking about research theory, methods, and software development. There's a system integration happening using design languages, and we develop the engineering framework from the steps requirements over design, product architecture, modeling, simulation, test, digital factory, to cost and energy analysis. So the whole product lifecycle in a digital manner, and there are different use cases. One is focused on automated design and digital factory. That's where I present today about automotive car bodies. We also look at gear systems for suburban train, for quadrocopters and multicopters, and balanced two-wheel scooters as educational use case. So a main part are graph-based design languages. When we have a graph-based design languages, we have some programming happening. There's vocabulary and rules which build up a design language, and there's this programmed by human beings on the basis of certain ontologies, abstract geometry, abstract physics, and so on. And then if this design language is existing for a product family, it can be compiled using a certain kind of software developed at the University of Stuttgart, Design Cockpit 43, And this is a compiler, and the result is a design graph, and this can be transferred in multiple data formats, which are generic, like for Siemens NX, CATIA, V5, MotionSolve. If you look at multi-body systems, finite element methods, or OptiStract radius, and so on. So there's a general information flow from the human definition and programming in the design language, then to a machine compilation and execution on the right side. And this is done by engineering framework, both based on unified modeling language together with graph-based design languages. Now, at this time, we want to focus on Geo-Station. So a Geo-Station is a station in the assembly line of automotive car body, and it's used to ensure position and orientation of several product components. So they are brought together. And if we look at the process, we first have requirements from the product. We have product components leading to a joining sequence, and then a production concept, which is the main point that we'll discuss here. So there will be the joint positions, and a setup and fixture concept. And there are requirements from layout. Everything needs to be accessible and reachable. So there will be interference objects and robot positions. From this, packaging will happen of this Geo-Station. There is very important collision detection. And so finally, we will get to the geometry synthesis of the home Geo-Station. One important point of this talk is the design rationale. A design rationale describes the reason behind the design selection and the decision, but also the justification for this decision. So which alternatives are considered and how are they evaluated, so that someone knows why something was decided, why something was selected. So if we look for the joining sequence, so the sequence, how the components are joined, here iterative search happens, and there are certain optimization criteria which build up the design rationale. This is accessibility and joining time. And here you see the exemplary definition of a joining sequence with the UML classes on the left side, and here the final assembly with two sub-assemblies. One sub-assembly consists of a reinforcement sheet that you see here and a thread plate, and the other sub-assembly is the component itself, which is the B pillar of a car body. The next step is finding the rationale for clamping and centering positions. So where do I hold this part, this B pillar, and at which positions do I achieve a safe centering? And here you see the UML classes clamping lock and centering lock for location. And here there are centering and clamping locations as seen here. So usually in a production concept, there is a joining plan. So where have the components to be joined, then a clamping plan, where are they held, and centering, how is their position realized. And in an engineering framework, a consistent representation of this is possible. Now, next step is to come to the real unit. So what we here have is, for example, welding guns. So here you see the genuine geometric interference object, which are really complicated, as you see here. And in order to allow a search for the best position, we work here with abstract and simplified geometric interference object in order to be able to find the optimal places for clamping and centering units. So how does this work? Well, we have a predefined geometry of a model. Here, for example, the B pillar. So we derive an outer contour, we create n edge points, and then we detect collision-free unit positions for clamping units. So what we already have here are some joining positions. So they are predefined because the joining positions need to be reached. And then we look for possibilities where to put a clamping unit. And so, for example, here, these 2 points were tested and found out, oh no, that does not work because there are collisions. And so it was found, okay, we have to go from these clamping positions to the other side to find a possible clamping unit position which will work. So using this abstract object, it's possible to find the optimum packaging model and also to store this decision which led there, the design rationale which is behind this packaging model, and to develop this further in the engineering framework to a complete physical model as you see it on the right side. Thank you very much for your attention.
Dear colleagues, my name is Stephan Husung, and I would like to welcome you to our presentation on integrating model-based design of mechatronic systems with domain-specific design approaches. The presentation is structured in 5 sections. After a short introduction, we present the relevant research questions. Then I will speak about the procedure, methods, and models on the different system levels. The presentation will be closed by an example, a summary, and a short discussion of the next steps. For the development of mechatronic products, their description using system theory is recommended. Based on this, products are described as models of so-called mechatronic systems. The introduction of system thinking implies a decomposition of the mechatronic system into subsystems that could be developed individually and finally will be integrated. Approaches for the development of mechanical subsystems are well known. The same can be stated for the other relevant domains. At the end of the development activities of the domain-specific subsystems, a detailed description of them must be available for the further product life phases. However, the domain-specific approaches and models often reach their limits when connected to the mechatronic system levels. Systems engineering approaches are placed on the mechatronic system levels and mainly support the decomposition of functions and system elements, as well as the validation of the integration. Therefore, it is often useful to extend the known approaches at the mechatronic system levels with system engineering approaches. Against this background, the following 3 research questions are discussed in the paper. How do systems engineering approaches help extending existing methodologies and methods to deal with different mechatronic and domain-specific system levels? Which added value do semi-formal system descriptions offer at the mechatronic system levels? And the third one, which information has to be exchanged between the different system levels and how to do that? The questions are discussed in the paper. I would like to present you a few excerpts here. Domain-specific approaches work very well as long as the functions can be implemented mainly by physical principles. On the mechatronic system levels, besides these functions, often logical functions are needed. Logical functions define, among other things, when which physical functions are active. These functions usually have complex dependencies and form complex effect chains. The handling of these logical functions and their decomposition is supported by systems engineering approaches. This is one reason for considering systems engineering approaches besides the domain-specific ones. The paper compares the different goals and constraints of the approaches at the mechatronic and mechanical system levels. On the slide, you can see a part of the comparison. It is easy to see that the goals of the approaches have similarities, but there are also differences at the different system levels. Therefore, according to the current state of research, the different approaches should be used in a complementary way. For this, interfaces between the system levels are necessary. The interfaces concern the methods and procedures, as well as the description of the system and subsystems, which are also compared partly in the table. The description of the system and the subsystems is done with different models. Important one and related tools are shown here on the slide. Between the models of the different approaches, information must be exchanged bidirectionally. When transferring information to the mechanical domain, these are primarily mechanical functions, interface requirements, as well as requirements for further decomposed properties. The combined procedure using different approaches on the system levels is explained using an example from precision engineering. Here, it can be seen that different decompositions on the mechatronic system levels are useful before the detailed development in the domain makes sense. The combination of system engineering and domain-specific approaches is becoming increasingly important. Interaction of the approaches must be clearly understood so that the approaches on the mechatronic and domain-specific levels can work together efficiently. A challenging question for the future is whether it makes sense to leave the different approaches in parallel or whether a merge makes sense. This is a question that I would also like to discuss with you during the session. I look forward to the discussion with you during the conference.
Hello, I'm Victor Romero, and I will present you the work we have done with Romain Pinquié and Frédéric Noel, for which we propose a survey of model-based design reviews, the current practices, and the future challenges. In the past years, we observed a paradigm shift from document-centric design, for which all the data produced around the design of a system are in a document shape, from a model-based design, for which each data produced is in a model shape. Depending on the community, there are a lot of different names for this kind of design. We will use model-based design using the definition from the INCOSY, for who the model-based design is the formalized application of modeling to support requirements, design, analysis, verification, and validation activities. Now we want to understand how this paradigm shift has impacted the design reviews activity. First of all, a model is an abstract view of a system. It relies upon a domain-specific modeling language, and so we can produce this model with different software in different languages. And it aims at helping to answer questions. For example, does the specification is complete or correct? We have there several examples of questions that models can help to answer. And how this paradigm shift, so from document-based design to the model-based design, has impacted design reviews. Mainly, we are interested in understanding the changes for the collaboration, for example, between experts and non-experts, and how to deal with models' interdependencies. In the literature, we can find some studies already interested in studying the practices during design reviews, but these studies are not interested specifically on these model-centric, model-based design reviews. And we also can find some prototypes around design reviews, but mainly around only one model. And more specifically, we can find mainly around the CAD model. And we found only one reference talking about specifically model-centric, model-based design review, and saying that when the design reviews are concerning only experts, the models are well used and efficient to help in design reviews. But when a lot of different stakeholders are impacted by the design review or are participating to this review, we go back to a document-based presentation with handcraft PowerPoints, for example, and then we'll almost return to a document-centric document-centric design review. Then our goal is to study the current practices in model-based design reviews, providing a survey, and we will present this result in the next section. First of all, about our methodology. Our survey is on model-based design review practices. We want to understand the practices, and is a 9-question survey in English, web-based, in order to propagate it in a lot of different communities. And our goal is really to elucidate the requirements, the required visualization and interactions capabilities to better support model-based design reviews. We distribute this survey through different in several associations or working groups, such as the Atif, Atlas, Smart, Design Society, also OMG, etc. Our goal is to aim a French community, but also an international community, academic researchers, but also engineers and managers from the industry, the public and the private sector, and mainly experts and non-experts of model-based design. Now we will present our results. First of all, about the demography of the respondents. They are mainly from academic researchers or engineers in aerospace and defense domain. They are mainly French, and we have half experts and half non-experts of model-based design reviews. Their current practices are 1 or 2 hours long design reviews. To collect the decision, to capture the decision, they use minutes or textual annotations, and they do model-based design reviews in various modes, for example, synchronous or asynchronous reviews. And the main goals of a design review is to validating the requirements, to understand a design in another way that they designed their own model, and also to verify a design against its requirements and to analyze the change propagation. Finally, the goal of our survey is to provide a list of recommendations and of future challenges on model-based design review research, and we want to provide a list of needs that future design reviews environments must have. So the last question of our survey was about the difficulties faced by engineers during model-based design reviews, and this question helped us to raise this list of recommendations. We think that design review environment must have a way to make the implicit interdependencies between models more explicit, more clear, and must allow to access the models in a unique design review environment without the loss of crucial information that today practice have. And these models have to be semantically transparent because of the difficulty to understand the language of another engineer. And the environment must provide an holistic bird's eye view, so in a place where we can visualize all the models produced around the design of a system. Thank you for your attention.
Hello and welcome to my presentation. My name is Dominik Wiechel from the Heinz-Nixdorf Institute in Paderborn, Germany, and I want to present my paper about the model-based effect chain analysis for complex systems. As you all know, the complexity in the development rises, for example, for the cyber-physical system itself, but also within the company, including all their processes and communication, and in the environment, including their market regulations or the supplier demands. And these elements are linked to each other, and cause-effect relationships has to be identified. Effects can propagate from one element to the other, which can lead to increasing costs, changes in quality, but also project failure. And existing model-based approaches only consider specific aspects of the system without including these upstream and downstream elements. And this leads to the following research question: how do existing modeling methods need to be adapted to enable systematic modeling and analysis of effect chains for complex technical systems? Therefore, we rate a 4-step approach And in the first, we made a systematic literature analysis. Then we made the synthesis of literature and developed our own method called the Mecha method and evaluated these within a company project with automotive OEM in Germany. In the first step, we identified 725 papers in the databases of IEEE, Google Scholar, and Design Society, and used KO criteria as well as a reading scheme to reduce them to 16 approaches. And these approaches have main characteristic, for example, the deliberated view. So just a set of elements is identified and modeled, as well as every effect chain has a starting point and an ending point, and between them there are other elements which are connected using traceability information. And the last one is that all these elements are connected using explicit modeling tools, but also modeling languages. Based on this synthesis, the definition of the effect chain is derived. So model-based effect chains of interdisciplinary complex systems are cause-effect relationships that are mapped using traceability and system element artifacts. But all these approaches have specific focus areas, for example, modular product architecture or the customer requirements. And this limits the representation of artifacts which can be used within the approaches. As well, there are some discipline-specific methods, for example, coming from the mechanical side or the software side, and not including interdisciplinary information. Based on these results, the Mecha method was defined, and this is a method which is divided into 4 steps. In the first step, the definition of the goal of the effect chain modeling. It is necessary to identify the system context and also the scope of the required system elements and their cause-effect dependencies, which have to be modeled. And this scope has to be clarified and defined as a goal and must be available for all interacting persons. In the second step, the dependencies and system elements within the delimited system section and over predefined system levels have to be identified. So as a result, the information to be modeled can be including, for example, information which are also there, like partial models, and also information about the granularity of the level of the effect chain. And this set, which is defined, can include also typical artifacts like requirements and functions, but also organizational and environmental artifacts like regulations. So the information to be modeled are identified, and then in the third step, these has to be modeled using existing tools and also existing modeling languages, for example, SysML. And there it is possible to at first customize the required model elements to include all the specific model information which are defined before. And afterwards, it's important to define which behavioral or structure-oriented diagrams can be used. For example, there's the possibility to use the IPO logic within the internal block diagram, which can serve as a central functional part of the effect chain. In step 4, the effect chains can be analyzed by different approaches, for example, algorithm-based impact analysis, but also expert knowledge. The evaluation was carried out on the context of a project on effect chain modeling for 30 systems of an automotive series of a major German automotive company, which has to fulfill the UNECE regulations, and the UNECE regulation 156 defines the software update management systems for these series, and this is necessary for the homologation of the series for the European market. So the impacts of changes in regulations or in the system components has to be analyzed, including their relations to requirements and functions. Therefore, we made workshops with different participants to identify the necessary data with the help of design structure matrices. And in the figure, you can see how regulations and their requirements are mapped to system functions in IBD. So the IBD is in the middle and is a central part of the effect chain. And the aggregation of the system functions represents the customer function. And additionally, the system functions can also be mapped to system components. So you have the effect changes coming from the regulations over the functions to the system components, including the organizational specific elements. And beside the successful application of the method, we use the feedback from the workshops to improve our method. So a finding was that the goal for the participants has to be communicated explicitly. And this is why the definition of the overall goal is our step one in the approach. And another second finding was that during the workshops, it remained fuzzy which data is relevant for the effect chain modeling. This was also included in our second step. The conclusion shows that our approach is based on the limitations and main characteristics of other approaches and should help developers modeling effect chains. And we evaluated this in a project with 30 systems. And the time effort for modeling was just 35% within our project. So the effort for the data collection validation was a lot higher. And we want to reduce this effort by automating and customizing our approach in the future. Thanks for your attention. And if you have any questions, please let me know.
Thank you and welcome to the presentation. My name is Martin Valdivia. I'm a research engineer at the Chair of Industrial Information Technology at the Technical University of Berlin. And I'm going to present an overview of our paper towards integrated safety analysis as part of traceable model-based systems engineering. As a short introduction, we can say that systems engineering is used as a transdisciplinary and integrative approach. So model-based systems engineering approaches often refer to the V model as an underlying development process. So there is a connecting point also related to safety analysis processes in which they can be performed during the system definition, decomposition, and analysis process that is on the left side of the V model. This is shown in the right figure in the red square. The intent of this paper is to describe a model-based method that considers this functional safety and socio-technical aspects during the early stage design process. The solution proposal that we have in this paper is to link virtual and hybrid prototypes. And then this is shown on the right figure, in which we can see that the system engineering process and the safety analysis process are linked to each other, coupled together. And then there's also a human system interaction from both sides, in which is performed by the hybrid prototype, in which the human interacts then with the machine itself. So the test person interacts with the hybrid prototype when the object to test is functionally defined already. This enables to test the system and the socio-technical behavior, including human-machine interaction and identifying potential risks. The system model here will be coupled then with a component and system risk assessment, and this takes advantage of the usefulness of the interaction between the different systems, such as changes management, or also the function just to trace back the whole design path. To do this, as shown in the figure on the right top, we are gonna connect an FMAI done in Excel with a requirements list also done in Excel. This requirements list with a system model made in Cameo System Modeler, and then this system model with a behavior model made in MATLAB Simulink. The connection of the FMAI to the requirements list is done through Excel hyperlinks. This can be seen on the figure on the right bottom, in which when you click on such a hyperlink, it opens another sheet with where the analysis is performed. The connection of the requirements list with the system model in Cameo System Modeler is done through an internal requirements synchronization tool of the system modeler that supports the functionality of like syncing requirements in Excel with the requirements list internal on the system model. Then finally, the connection of the Cameo System Modeler with the behavior model in MATLAB Simulink is done with the use of a third-party software that's called Zendaya, tool to trace back from between different models. The overall integration achieved by connections is achieved by connections through the systems engineering process indirectly, which means that it's not like it's a broken process, but we're going to get back to that later. Our use case is a safe door opening system, also known as the SDOS. It is a driver assistance system for cars that gives a warning when a dooring accident might occur. Dooring accidents are accidents where a cyclist crashes against an opening car door. The system consists of 2 warning light systems, a vibration signal inside the door handle, a sound warning, and a motor for door closing. Here MATLAB Simulink is used for the warning signal generation as a response to virtual sensors that detect the cyclist, of course also virtual cyclist, and DSpace is used for car surrounding visualization. There are 3 different scenarios that are modeled within different door opening angles that simulate different behaviors of the system. And socio-technical interaction between the cyclist and the driver can be tested with this use case. Here's our 2 images. The left image, it's an experimental setup of the SDOS, and on the right we can see the system with a test person. As evaluation and conclusion, we can see the traceability between corresponding design artifacts from requirements until the test could be demonstrated. When applying the testing modes, the functional change of the products were tested, and this revealed connections between the elements and models. There were also some limitations by the use of tools themselves, like Excel is not an optimal tool to perform an FMAI nor a requirements list. And there are also limitations related to cross-tool traceability, since the applied solution is a combination of different approaches like internal supported linkage or add-on supported linkage. The complete design path needs to be followed to trace back to initial artifacts. As a summary and outlook, we can identify a potential that supports like an automation of the trace link. This could improve acceptance of the tools and bring traceability benefits at lower time cost for engineers. And the following steps we identified here are centralizing the connections within the cloud, not using just one tool for all the trace links. Use of different tools for integration of different models, better tools that are more capable of doing this analysis. We want to use improved software packages to quickly establish links between objects, and also to describe the influence of errors of function and systems elements on the quality of the product.
Okay, well, thank you very much to all the authors for providing us with these very nice presentations, and I couldn't help reflecting how well integrated these presentations have been in this session, because there have been some very common themes, and I couldn't help as we were going through thinking of how the methodology discussed by one of the presenters would apply in the context of the problem discussed by some of the other presenters. So I guess this would provide us some very good opportunities for having discussions across the presentation. So just use an example. So Ralf was talking about the rationale and the use of graphical languages to take that rationale, and then Stephan has been talking about logical functions, and then we talked about the cause chains, cause and effect chains, all supported by the same model-based systems engineering environment. So I celebrate this fact that we quite often use different language to denote the same sort of tasks, and that is to manage that decomposition of systems, ensuring traceability, and also capturing the rationale which ultimately explains the propagation of causal effects, or effects chains. I've also noted that a couple of presenters actually formulated future research, and I think, Stephan, you have, in particular, you actually asked a question which you thought would be useful, a point for debate. So I'm going to suggest that we're going to come back to that, but in the first instance, it might actually be useful to go through the questions that came in the chat, and invariably these questions came in a chronological order, matching the presentations. So I'm going to go to the top of the chain, and Christian, I see you here. So you had a question for Ralf. Do you want to ask that?
It's just a question of interest. You couldn't tell every detail of your research, but I wasn't quite sure how you find the clamping positions. Is it done by the user or semi-automatically?
It's nearly done fully automatically. So I'm happy to meet you here, and also thank you for this question. And in fact, this is the dissertation of Andreas Zech. He is currently doing his dissertation at University of Stuttgart, and he is mainly working on the algorithms which will allow us to automatically find these positions by using the simplified geometrical elements. But it's planned to do it automatically.
Can I just ask a question, and that is that you talked about the rationale, and what you've illustrated without articulating it very clearly is that you actually have some sort of hierarchical decomposition going from some objectives or key characteristics or critical characteristics for the part, and then you go to the design of the process. So, for example, as you're dealing with, as you come with finding the optimal position for the clamping devices, do you go and update the rationale? Is there a need to go and update the rationale? So the upper level.
I mean, the upper level, usually not. It's more the lower level of the station design. This rationale has to be captured, but the more abstract rationale will be the same as long as it's possible. I mean, there's still the possibility that we find out, these joining positions and clamping is not possible. And then you have to go back even to the design department and say, can we have other joining positions? That's not happening very often, but in theory, it could still happen.
Okay. I was thinking more of the fact that what you find from searching what's the optimal clamping position or fixing positions, you actually come to extract some rules which are actually useful to feed for future optimization exercises, or make heuristics that you want to feed forward.
Yeah, that's this dissertation of Andreas Zech, and especially these heuristics where you suddenly have to jump to the other side of a part. So they are sort of novel because there are some problems that you usually don't have in optimization.
Okay, thank you. Can I just ask, let me just check, are there any questions that someone would like to ask Professor Ralf Stetter? Okay, I guess then let's move on to the to Stephan, Professor Stephan Husung. So we have a question from Dominik. Dominik, see you there. Do you want to ask the question?
Yeah. I already read it, so I can answer directly, I think. Thanks for the question. Yeah, that's a very interesting topic. I think maybe let me start on a different point. I don't like the word logical element, but it's very typical in systems engineering. But logical element in many cases is more or less a more abstract description of a component, more or less like a generalization or something like this. This is used behind the logical element. The logical function, I don't know if it is the best word for it. comes from another direction. Normally, especially in classical product development, we have functions, for example, transfer electrical to mechanical power or something else. And this is more or less a function which is directly related to a physical principle, in this case, transformation process. And very often, and this is a limitation of current methodologies, we don't consider this dependencies between these functions. This means, for example, when is a function active? Do we have some decisions between functions, go left, go right, something like this? And this is what I call logical function. We can discuss this. I'm not sure if it is the best word, but currently I often use this logic because it's very good understandable, especially when you speak with people coming from software domain. They understand logical functions as functions making decisions about physical functions.
Okay, thanks for your answer. I think this is a really interesting topic because coming from different disciplines, there's a different understanding at this point. And I think I just asked this because at the presentation there was the definition of logical functions, or the elements were named like that.
Yeah, it's why it's normally used as logical elements, but I don't like this.
Okay, fine, thanks.
Yeah.
Yeah, okay, thank you. And Stephan, can I just ask you to maybe restate the question that you would actually like to have as a debate?
Yeah, that's very good. Thank you. As we discussed in the paper, currently we see a lot of applications of well-known design methodologies, and they work very well, especially when you're very close to physical realization. Because at the end, we need a very detailed description of the system and so on. And when you go to the higher levels of the system, then we don't have the aim to find a final, very detailed description of the system on this level, because the motivation is more or less to decompose the functions, to make something like a federation of the subsystems, to define integration steps, and so on and so on. So the motivation or the objective is very different. And currently, we have this gap between these methodologies. We have this more abstract methodologies at the system level, at the mechatronic system levels, and then we need a very detailed methodology and detailed descriptions at the end in the domains. And currently, we have this two approaches or several approaches, more than two approaches. And my question is, should we try to find an overall methodology to combine them, or should we leave them separately? Currently, I'm not sure, but I see a lot of misunderstandings when we speak about these different methodologies. Yeah, this was my question. I want to discuss with you because all of you are experts also in this field. I know, especially Felician, in your work, you have the same challenges. And I think, Dominik, I know this work from Paderborn also, you discuss similar questions.
Yes. Yeah, indeed, and I suggest we're going to come back to that discussion. I think the one question which I'm actually looking is reflecting at the way you presented both in the paper and you've articulated it just now. Is it the case that we perhaps need to is the solution to actually come and sort of focus on that logical systems analysis or logical layer or functional layer, as I've seen articulated by several others? I think, Ralf, you have talked about the functional layer in a different presentation, and necessarily when we're coming at that level, what's very important is to have completely solution agnostic articulation of the function. And is there a point that one of the key things that we need to concentrate is actually the description of the functions in terms of metrics and characteristics, which
definition, of course,
and basically actually come with a richer taxonomy for these characteristics, and from there on also for failure modes that are associated, or failures that are associated with these characteristics.
Yeah. Of course, this is a very important puzzle part. Yeah. Yeah.
Okay, thank you. Can I just ask Clement? I've seen you have put your hand up. You seem to have put your hand up. Was that
no.
Just a
well, I have one reflection on this about integrating methodologies there. I think you need to have a continuous flow, and I think we should talk about one single methodology from different perspectives. But I think that means still some research work to be done to have an ontology which covers everything well. And I think the level of granularity or abstraction changes definitely for the concept level to the detail solution. And I think we need to be able to play at these different levels.
Yeah.
The model at the different levels.
Indeed. Christian.
You're still muted.
Yeah. Thank you. I wrote it in the chat also. I think we still have big problems with, to link all the, let's call them physical related tools that we already have since decades to models in model-based systems engineering. And that hinders the flow of information that Clément was talking about.
Yeah.
That's my opinion.
Also.
Yeah, it is indeed. And I think reflecting on my experiences, the reason we have that is a lot of the simulations in model-based systems engineering and general building of models in MBSE is done retrospectively. After the system is designed, we build a model, or after we have a concept of the system, we build a model, and then we simulate that model. Whereas thinking about the logic is something that you do when you think about, let's say, designing a feature for autonomous driving or driver assist, taking the automotive example. And there is a level at which you're just thinking about designing that feature where you actually just think about the sort of pure logic across the different disciplines that would have to work together. And at that level, you don't actually have the simulation. And the problem is that quite often people rush, or designers rush to get to that point where you have a concept which you can model and simulate. And I think the question or the way I see the question is, well, should we actually start to come with a more supportive approach to that initial sort of capture of the logical layer, such that we can support the top-down decomposition and in a traceable way.
Mm-hmm.
I think that's a thing, because that would also do something which, again, in my experience, is very important. In particular, when people come with new features, innovations, and so on, you can spend a lot of effort to design and develop something that then you realize it doesn't work, and then you come and think, well, if we actually done a slightly better job at the sort of the logical level thinking and analysis, perhaps we could have thought from the beginning that, well, that's something that is perhaps not worth spending much time.
Yeah. That's one of the important points. You have different objectives. And if you start very deep dive analysis or synthesis on the higher system levels, you will fail. Because then you don't have this big overview about all the necessary elements and functions. And this is, besides the models and tools, I think one of the main challenges.
Yeah. Thank you. Dominik, I'm tempted to suggest that we move on to discuss the other papers, and then this is a topic that I think is very well worthwhile coming back, because I think it would be useful to maybe bring some of the viewpoints from the safety features and so on. So we have a few questions for Victor's presentation, Victor Romero's presentation. So Christian, I think I'm going to invite you again to articulate the question, because you've put a very nice question there.
Yeah, thank you very much. I wasn't first apologize for misspelling your name. It was too quick. I wasn't sure about the participants of your survey. Were they talking about model-based design reviews or just design reviews? And maybe if I may add to that question, what is this specific advantages of model-based design reviews? We have some experiences, and the people doing actual design reviews, they are not interested whether it's model-based, virtual reality-based, or whatever. They just want to do their design reviews. I mean, what is the advantage? Getting it earlier or what?
Thank you. I was intrigued by the same question, and maybe Victor, if you can start by actually sort of clarifying what type of models. And
I'm not sure if I have understand well the question. The question is what are the advantages of model-based design reviews versus design reviews? Okay, I don't know if there are some advantages, but I think that it's more than using models is an advantage in the design process in general. And then if we use models in our process, we will have to review these models, then to proceed to participate to model-based design reviews.
But I mean, so are you reviewing the models, or are you carrying out design reviews based on models?
I think that we are reviewing the models, and through the models we are reviewing the system we are designing. Well, that's what I thought.
So one thing I was surprised is that the sort of the quality of the models was not because in my experience working with people from industry, the key thing when you actually do a design review based on the models, the question that comes all the time was, what's our confidence in the model? That is usually the first, what's the maturity of our models? And that's, in my experience, is the first thing that usually comes around the design review.
Okay, I didn't take it into account.
Felician, the interesting question is why we don't ask about the maturity of the documents.
Indeed, yeah. I mean, I take it that the documents are go with the model, because you have models, and but then even having something like an FMEA, you can think of it as being a model, or it's part of it's a document that's associated with a model. The requirements are also associated with the model. Christian.
Yes, I'm a little bit older, and I can remember design reviews with drawings. I mean, these are also models of a future product. So there must be some sort of advantage if we go to model-based design reviews.
Yeah. So I think, Victor, part of the question, the reason we asked the question is, at least for me, and I had to read through the paper as well. I wasn't quite clear what are the models that you review, or that question wasn't very clear. I was looking at the question from Ralf, which was, do you include?
Yeah, I think, Felician, it also, because we had this discussion about design reviews before and how long they could be. And I was happy to see that you have analyzed how long they were. I think it was mostly between 1 and 2 hours, which I think is rather sensible. So I was rather happy to see this. But did you also ask how often they reviewed the design?
No, unfortunately, after I closed the questions, I closed the questionnaire, I felt that we are missing some question, and this is one question that I wanted to answer also, but we didn't. But we have an answer to another question similar, is that they participate to design reviews during all the design process, to model-based design review during all the process of the design, from the conceptual phase to the production phase. They still organize this kind of reviews.
Mm-hmm. So it goes all along the process.
Yeah.
And the other question, did you see or did someone make clear that mechanical things and software things were reviewed together, or are these reviews usually still separate?
I'm not sure if I understand well the question. For me, the design, the model-based design review we ask about is like reviewing all the models produced. So it can be, models produced from a lot of different softwares, but we are not sure which one they are using or.
Yeah, because the question, I think it's even we all, I think, agree for mechatronic products, this belong together. I think in many companies, they still do it separately. On the one hand, they do a review of mechanical things and electronical things, and they do another review of software things. And I think with this community, we could work to bring this together.
Yeah, I cannot find any software linking all these models together. And in the answer they gave in the questionnaire, in the survey, they said that they show the relations between the different models through PowerPoint slides, just during commenting the interrelations or. Yeah.
Thank you.
Victor, could you comment briefly on the question from Stephan, and that's around the traceability? So the question is,
yeah, the traceability is the traceability between, for example, two versions of the system.
The several elements of the system. This is, from my point of view, one of the criteria when you speak about model-based description, that you have atomic elements and traces between the elements. And this is a big difference to document-based working.
Okay, so the equivalent in another model of the same object or the same design system?
Now, for example, Christian said he started to review drawings. If you have, for example, a description between the different phases and the relations between the phases, then this is a more or less model-based description of this product, like we have in 3D CAD systems. When we speak about documents, for example, about requirements, this could be a Word document with 1,000 requirements. If you have atomic requirements and have relations between the requirements, then we speak more or less about model-based descriptions. Or you have a drawing with a function structure. Then this is more or less a document if you don't catch each of the elements and the traces between the elements. But if you have atomic elements, for example, like in a SysML model, the activities and the traces, then you have such a model-based description. And from my point of view, this is a big difference between document-based and model-based working.
Okay, so we asked a question about the relation between the models and how the designers deals with these interrelations and how they can make it explicit to show them. And I think that can answer the question. They find a lot of difficulties to make them explicit in our survey.
Okay, thank you. Thank you very much. I'm just keeping an eye on time, and we have a few more questions to address here. Thank you, Victor. I think we might come back to this topic of traceability in particular. Stephan, do you want to go and word your question to Dominik?
I have a little bit if it is impact analysis, maybe top down from requirements to the last elements. So this is what I normally call impact analysis to the system, or to speak about effect chains. This means in German Wirkkettenanalyse. If you speak about the effect chain between one inside of one element or between elements at the same system level, and then you discuss, for example, you have an input value, for example, a signal or physical value, and you want to check what is the output at the end of the system. And my question here was, which concrete effect chain analysis method you used here, because maybe there are different approaches.
Yeah.
At this point in this paper, we presented an approach for for modeling, a model which can be analyzed. So the main important thing is here that we try to help the experts that they get a method where they can say, okay, I need these elements and I need these dependencies, and then I have to, for example, write a little SysML profile to get these information inside my model. And this could be analyzed by algorithms. In this point, we made it with the automotive OEM in Germany, and they just use their expert knowledge for the analysis. But coming to your point, I think we are making a research project in Germany called Impact, and there we try to build model-based Auswirkungsanalysen or impact analysis with the main point at this. So I think that it's important to decide that in this paper we just presented how to model the perfect model for your analysis on different layers. In this point, at the functional layer with ports and connectors between the system functions, and with the link to the regulations like certification requirements. But we don't go any deeper at this point. But the method is defined for finding the right model, and afterwards there need to be some algorithms or expert knowledge. But I think we could also talk about later at this point that there are a lot of impact analysis algorithms and also methodologies.
That's very good. Maybe in September I'm in Paderborn. Maybe we can also make a visit at the department. I can also speak with Iris.
Yeah, sure, for sure.
It could be interesting.
I think so. Yeah,
thanks.
Thanks.
Thank you. Ralf, do you want to ask your question? So I have a very similar question, but I'd like to see how your question and the answer from Dominik goes.
Okay, yeah. So my question is rather also aiming at your definition of what effect change do you analyze? Because I think that you mean the effects change within the product, but this can also be within, for example, a production site, or they could even be at the development process. Is this restricted, or is there an underlying definition for this?
At this point in the title, we say for complex systems, so we focus on the product. But I think in the end, it depends on the information you want to analyze. So it would also be possible to analyze process information or the other information you mentioned. But it just depends on how well can I integrate my information into my overall information model or system model in this case. And for example, your point with the rationale, I also think that it would be possible to include rationales into some kind of system model and analyze the impacts. So I used SysML as modeling language. There you are able to customize your language to get to the point to integrate other information into your impact analysis.
Okay, sounds interesting.
So my question, thank you very much, Dominik and Stephan and Ralf, for your questions. I mean, I was reflecting on this again, because you can talk about cause and effects between the system levels of abstraction, but then the pathways of propagation are quite often at one level at the same level of abstraction. And my question is, well, how do you capture those pathways of propagation of effects? I mean, having a reliability background, I tend to talk about fault propagation, because quite often the effects are either the realization of a function or the propagation of faults through a system, which ultimately lead to the lack of realization of the function. So you do mention, I mean, do you? So how? Because what's very important and actually capturing those pathways of propagation is difficult. So do you use what sort of methods do you use for that? Do you use sort of analytical methods? Do you use simulation?
Yeah, I would start with, for example, an RFIP logic coming from requirements, going to functions, logical elements, physical elements. So like for every discipline, I think it's understandable. And at each layer, you have to define your elements, for example, requirements, and as well as the dependency in between this. And we saw in our project that each layer is very difficult. For example, also at the requirements level, it's not that easy to identify each dependency between each requirement and the propagation. So which type of dependency propagates? For example, does a refine propagate, or does a abstraction or allocation propagate? And we try to use NLP for identifying the implicit dependencies between elements, and also trying to bring the user or the expert to the point to define explicit dependencies between the elements, for example, in the modeling tool. And in the end, as you mentioned, there are different perspectives for your propagation analysis or the impact analysis. And in my point of view, it's the most important thing to define at first the elements you want to analyze, and all other elements should not be mentioned in your model, because the model explodes at this point of view. And
do you use things like, well, interface analysis or design structure matrix type tool?
Yeah, in this point, in the paper I mentioned that we used design structure matrices between every layer, and go into the workshops with the experts and ask them, okay, is there a dependency? In this case, just a bidirectional dependency without any weight.
Right.
And we just modeled it afterwards in our system model.
Okay.
And this was the main point, but at this point, it's also hard to get the implicit knowledge out of the heads of the experts, and some things are missing, and then you have to corrugate your model often.
Thank you very much. And I'm coming now to Martin. We have, I'm just realizing we just have a few minutes left. So I think we had, Martin, we had a question from you from, I mean, there was the reflection from Christian Weber that there is very close connection between your paper and, well, in fact, at least Stephan's paper, but I would say with several of the others. So now I'm gonna articulate your question. So the question there is your paper representing prevention systems, so multiple scenarios in a single model, so you cannot unmute yourself.
Can you please try refreshing? You were able to share audio earlier, right?
Yes.
Can you please try? He tried refreshing. Okay, we'll see him back in a second. It seems like your system is not recognizing your microphone. Please check the permissions in the...
Maybe if you write an answer into the chat, how long can we see the chat?
I can see. Yeah, it's okay. It's okay. Can you repeat?
Yeah. Okay. So the question is the question from Noel. So if you go up in the chat. So basically.
But Martin, we can hear you now.
You can hear me now. That's perfect. Then thank you. Thanks for your patience. I am struggling a little bit with internet connection and everything, but let's go this ahead. So, yeah, well, the paper is based on it's one model that has different scenarios, but depending on, I mean, the model detects sensor input. Mm-hmm. And it can process themselves as, for instance, based on different door opening angles. The system behaves different if the door is entirely open and if it's closed. and also has different behaviors based on the distance of the bike rider to the car itself. So I'm not sure if that answers the question. Presenting prevention systems, yes, it is. And for multiple scenarios in single model, yes, it is as well.
Yeah, I think it does answer the question. A related question, well, sort of related question I had is, because you talked about requirements, FMEA, and then you went into the MBSE and simulation. And my question is, did you actually use the FMEA to drive the experiments that you've run on the simulation to validate?
The FMEA was performed basically to identify the hazards of each component, and then based on the simulation, it's more a traceback to see, okay, this component may be if this component fails, it's more critical for the overall system than if other components fail. And this also based on then the behavior of the human and the machine. So it was part of the design. It was one of the first parts of the design, and we tried to, this would be a first step to then make redundant systems. So in order to prevent stranger dangers for the bike driver, for example.
Right. Okay. So yeah. Okay. So you have used the FMEA largely for understanding the failures of the component rather than focusing the FMEAs on function failures, which
yeah.
Right. Okay, I understand that. Well, and I see that Ronald is satisfied with your answer. I'm afraid we're out of time. I have sort of noticed the comment about follow up to this discussion. So I have to say, just want to thank everybody for the engagement with the session. I think we had some really good discussions. Personally, I feel that there were quite a few things that we've started we didn't quite finish. I like to see the sort of some of the things being picked up and followed up after the session. I would almost like to suggest that maybe we can start to create a community, because I think there have been some very nice challenges, and this point that going for model-based systems engineering raises some quite fundamental questions about how do we integrate traditional design with the MBSE approach, which is needed in order that we more effectively and more timely address the issues of complex systems of systems features, which really what modern problems in well, not just automotive, but I would say with all robotic autonomous systems seem to revolve around these problems. So unfortunately, I have to close this session. Give time for a break before the next session. Thank you very much, and thank you very much, Christian, for your comment. And what I'll do is I'll try to send a note to colleagues that have participated in this session, with that view of maybe taking this discussion a little bit further. I think this would be very nice and very useful.
Thank you.
Thank you very much.
Thank you very much for your sharing, exploration. Thanks to everyone.
Thank you.
Bye.
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 Bye-bye.